This is going to be a presentation on membranes and masks. So what is a respirator? This basically our first line essential defensive weapons. We cover our mouth and nose, and they are meant to prevent the passage of particles. Specifically, the one I really want to talk about is this N95 respirator, and you will see why. It's designed to achieve a very close facial fit, and they are commonly used in healthcare settings, and they are tested extensively. So to be able to manufacture this type of mask, one is required to have a series of tests passed. Now, it's originally developed for industrial applications. And N95 means that it's supposed to stop, the mask is supposed to stop 95% of the particles about 0.3 micron, 300 nanometer particles passing through the mask. There are also N99 and N100 respirators. N99 stops 99%, and N100 stops 99.97%. So the key here is 0.3 microns. Now, if you look at this course, if you look at this COVID-19 virus, and this is from the isolate of the first patient in the US. What you see as blue here are the virus particles. This is what the virus looks like when it's illustrated. And I'd like you to note that this is about 120 nanometers in diameter. So we are using masks with pore openings of about 300 nanometers to try to prevent the passage of nanoparticles, these nanoparticle viruses, which have diameters of about 120 nanometers. The shape was interesting, the spherical shape and the corona surrounding the virion, etc. And I wanted to find out if there are other viruses which are similar in structure. And it turns out, for example, if you look at the measles virus, that's again about 120 to 250 nanometer, and the same type of corona arrangement in conjunction with the spherical shape. So we are again seeing that this specification that we have for the state-of-the-art N95 mask really under normal circumstances should not be able to stop the virus passing through because the virus diameter is relatively small. So something to be concerned of. How does the mask work? How does this N95 work? There's basically two layers, and sandwiched within this layer, there is this membrane layer, which is the key. So it's the membrane layer which controls the passage of particles and nanoparticles through. This is an SEM view, and I'll show you others of this membrane view. It is basically polypropylene fibers and nanofibers manufactured through a process called melt blowing, which I'm going to talk about extensively. But here is again the membrane layer you are looking at. This is 2 micrometer. So we have this is the diameter size distribution, the diameter distribution, and we see that there's basically fibers between 500 nanometers to about 2500 nanometer, with a mean somewhere around 1000 nanometers. And the filtration mechanism, this is from a report of the National Academy of Engineering, basically has 3 actions. One of them is the fibrous mesh. This non-woven mesh presents a tortuous channel through which particles, the nanoparticles need to go through. So this tortuous path, they call it inertial impaction. The other one is, this is like colloidal particles hitting each other, this random walk that one encounters with colloidal particles less than 1 micron is called diffusion. So again, it's related to the porosity of the fibers and the thickness, etc. And then there's also electrostatic attraction, which is associated with this mesh. This is the membrane layer functioning to stop the passage of the virus. Now, here's the problem. This is really very telling. China produces 20 million masks daily, 20 million, and there might be a zero missing. I thought it was 200 million. But only 600,000 are N95. So the most valuable mask, it's not possible to just ramping up production. The reason is the bottleneck is the membrane layer. So we'll talk about this extensively. It's a melt-blown fabric. There's a global shortage of it. There are very few countries which has it. For example, the US capacity is something like $1.65 million. This is 3M per month. And the machine costs a lot. It's $4.2 million. And even if you order one, you have the money to order one, it will take the order 5 to 6 months to be executed. So this really is the bottleneck. And this is really how I got into this picture. I was asked to serve as an expert witness. I was offered this position for patent litigation a few months ago. And I turned it down. Obviously, I'm very busy. But then I said, why did they call me? So when I looked into the process, the patent was about this melt blowing process, which we are going to talk about. It turns out this is the process to manufacture the membranes of the N95 respirator. And it turns out I do have a competing technology for manufacturing these membranes. So let me start with the conventional method. This is, the method that's used to manufacture these meshes. One starts with an extruder. So I'm going to talk about what an extruder is. There's a mixer, there's a metering pump, and then basically one goes into this melt blowing die. And then the fabric that's generated, the non-woven mesh that's generated from here is collected via a drum collector. So the extruder part is relatively easy. We can handle this very easily. This is one of the extruders that we have built in-house. It's called the universal. it can do counter-rotating, co-rotating, twin screw, single screw, fully intermeshing, tangential, etc. Our own design. And we have done one for the US Army, for example, with everything opening up, the die detaching, the barrels detaching, etc. So this is relatively easy technology for experts like us. We can do mathematical modeling. We understand exactly what's going on. So the technology that you see on the left-hand side is the most flexible manufacturing method, and the one on the right-hand side is one we designed on purpose to be able to handle relatively small production sizes. So the extruded part is no problem, right? We saw that. So where is the challenge? The challenge comes from here. So this is the so-called melt blowing process. There's a die, the polypropylene melt goes into this die, and then out of this die, fibers come out. And of course, if you don't take care of the problem, these fibers will just coagulate with each other, stick with each other. So you have to prevent that and you have to control. So the control is done through this specialized hardware in which the fiber is extruded through this hole. This is from one of the patents. So the material, the polypropylene melt, comes through this hole, and then surrounding this hole coaxially is airflow coming in at high temperature so that the fiber is guided so that it's not going to stick with the next one on the side. So you see these holes side by side. And you can imagine the challenge. I mean, you are trying to control the motion of fibers through impingement of air, and this is really not a very easy process to handle. So what they do, for example, one of the newer patents, you have these heating elements, cartridge heaters associated with each hole. I mean, this is like, forget it. This is an extremely difficult process to control. That's why it's so difficult. So what's our technology base? We can fabricate non-woven meshes and nanofibers at any porosity, pore size, fiber diameter. We can do solution or melt processing. We can incorporate particles and nanoparticles. These can be antiviral particles, and the technology can generate functionally graded meshes, multiple layers with different antiviral particles. So here is the extruder part. So we are using this portion just like they do, but instead of a melt blowing die, what we do is we incorporate a head which is associated with electrospinning. So what we do, we apply a high voltage, 30,000, 40,000 volts between a spinneret and basically a conductive plate. And basically we generate fibers coming through, and we can do this at any porosity, etc. Now, the nice thing about our technology is we can do multiple nozzles, so we can increase the number of channels which generate these melts. And we can put in, again, rotating drums, surface, etc., so that we can orient these materials. And we can increase these number of nozzles indefinitely. For example, here you see 20. So this is something you need to ramp up the production rates. And you can control the thickness distribution, porosity, and you can control the degree of orientation. So here's Hermann's orientation function between isotropic to anisotropic particle or fiber orientation. So you can go from this to that, any degree of fiber orientation is possible. The nice thing about our production base is that we can also work with all types of clays and nanoparticles and nanotubes, etc. And the extruder part allows us to disperse the material very well. So this is twin screw extruded, this is batch mixed. You can see that we can achieve significantly better dispersion. So you see the one here on the left-hand side, clustered and then dispersed on the right-hand side. So it's very well dispersion of particles followed by electrospinning. So these meshes are done very nicely. Basically, the last portion I want to talk about, which gives us an advantage, is functional grading of these meshes. We can basically incorporate particles, different particles or concentrations as a function of time with this process. So let me talk about that for a second. For example, we generate the mesh, and then the mesh is incorporated, say, with different concentrations of tricalcium phosphate. This is the ceramic used in tissue engineering applications, which we have a lot of expertise with. So part of the mesh could be free of particles, whereas the other side could be filled with particles. We can also do interface tissues. For example, in tissue engineering, we can have one differentiator go down in concentration while a second differentiator goes up in concentration. So we can generate cartilage-like tissue on one side and bone-like tissue on the other side. So functional grading is really very important. So here's another one. These we had called nano Bursa fibers. So carbon nanotubes containing different types of metallic particles. So the mesh we generate contains different types of particles. This technology is directly applicable then to antiviral particles being incorporated into these different parts of the mesh. I'm not sure whether this is going to work for this SARS-CoV-2 virus or not, but at least for different types of coronaviruses in the past, some zeolites and ion exchange resins, etc., in conjunction with principally copper and silver salts have worked effectively. Now, the other thing I want to mention is that the technology has the capability to do hollow fibers. Remember at the very beginning, I said that just using polypropylene, this technology they use called melt blowing, they generate these fibers, but the fibers are not porous, are not nanoporous. Whereas if we incorporate pores like this, basically what happens, I mean, look at this. This is 100 nanometers. So if you have particles, say, or virus particles, which are smaller than 300, our fibers should be able to capture them and hold them within the fibers so that they won't be able to diffuse out of this mesh. So let me finish off basically by indicating that we have the capability, we have some very interesting technology which competes directly with this melt blowing process, and we have advantages because we can manipulate fiber sizes very easily. We can do solution and melts. One or the other, we can do hollow fibers, and we can incorporate particles and nanoparticles. We can disperse them very well also, and we can do functionally graded meshes, different layers containing different types of antiviral particles. So with that, I thank you for your attention.
Thanks much, Johan. Okay, I have a couple of questions.
Sure.
It's a beautiful work. And now it appears that to increase the filtration efficiency of virus particle, and one would imagine that you need much smaller pore sizes, so to speak, right? But I thought that we also need to have a balance between comfort of the person who wears it.
Yeah.
Versus the filtration efficiency. And how do we strike the balance? That's my first question. My second question is, the viruses are negatively charged, right? And then maybe using electrostatic attraction mechanism might also be a very good way of increasing the filtration efficiency, even with a large pore dimensions.
Very good question, Sani. Number one, in terms of capturing viruses that are smaller than a certain size, these hollow fibers, which I showed, is really the way to go, because the porosity is governed by the pressure drop through this mesh is going to be principally affected by the pore size and porosity distributions. So there's so much you can do, otherwise you'll suffocate, right? If you overdo it, no air will come through, and basically you'll turn blue in no time. So there's a certain limit as to how much you can reduce the pore sizes. But the ability to put the pores directly into these fibers changes the situation. So the overall pressure drop is not affected. So you still have the same volumetric flow rate versus pressure drop relationship in this nanofibrous mesh. But at the same time, your fibers are becoming capturing mechanisms. And the virus could basically would basically be trapped within the nanopores of the nanofibers. Of course, it's possible to charge them any way you like.
Okay, and I got a question submitted from the audience. So the N95 mask making process is time intensive. How long does it take to make the nanofibers in this application?
Yeah, it depends basically on how many nozzles you have. It's the electrospinning dynamics which controls the flow rate out of each nozzle. So basically what that means is that, I mean, you cannot push the material through with an extruder and expect the production rate to increase. It won't. So basically what's going to happen is that depending on the voltage we are applying, the distance of separation between the conductive plate or drum versus the tip of the nozzle, and also some additional parameters, including material parameters, the electrospinning process is going to define what the flow rate through each nozzle will be. But if you have, for example, 20 nozzles, which as I showed you, you'll end up with 20 times the production rate associated with a single nozzle. So instead of 20, if you have 200 nozzles, then again, it's going to be 200 times the regular. So for building a mesh, let's say with 500 microns in thickness, with these multi-nozzle spinnerets is not a very difficult problem.